Neptune was found by an equation, not by a telescope, not by chance, not by a patient astronomer scanning the night sky, by math. In the 1840s, astronomers noticed that Uranus wasn't moving quite the way it should. Its orbit had tiny deviations, small, persistent irregularities that didn't fit the models. Something was pulling on it, something further out. Two mathematicians, one French, one English, working completely independently, sat down with Newton's laws of gravity and calculated where that something had to be. They predicted the mass of the object, its orbit, its position in the sky on a specific date. They were right. On September 23, 1846, astronomer Johann Galle pointed his telescope at the coordinates Leverrier had given him. And there was Neptune, within 1 degree of where the math said it would be. It was the first time in history a planet had been discovered by pure calculation before it was ever seen. And what we found when we finally looked closely, just once for a few hours in 1989, was a world so violent, so strange, so full of contradictions that it remains one of the least understood objects in our solar system. By the end of this video, I'll tell you about something Voyager 2 detected at Neptune that 35 years of analysis has still not fully explained. Let's go. Neptune is the furthest planet in our solar system, 4.5 billion kilometers from the Sun. So far that sunlight, traveling at 300,000 kilometers per second, takes 4 hours and 10 minutes to reach it. By the time you see Neptune through a telescope, you are seeing it as it was 4 hours ago. From Neptune, the Sun looks like a very bright star, nothing more. It provides roughly 900 times less light and warmth than it does on Earth. And yet Neptune is not a quiet, frozen, passive world sitting at the edge of the solar system. It is the most dynamically active planet in the outer solar system. It has the fastest winds of any planet, anywhere. It generates 2.6 times more heat than it receives from the Sun. It has a storm that appeared, vanished, and reappeared in a different location with no warning and no explanation. And its largest moon orbits in the wrong direction, on a path that is slowly decaying, heading toward a catastrophic collision with the planet in approximately 3.6 billion years. Only one spacecraft has ever visited Neptune. Voyager 2. August 25th, 1989. A flyby lasting a matter of hours. Everything we know about Neptune, every storm, every moon measurement, every atmospheric data point, comes from that single encounter, combined with Earth-based telescope observations and, more recently, the James Webb Space Telescope. One visit, 35 years of analysis, and we are still finding things in the data we can't explain. This is Neptune, the planet at the edge, the planet that was found before it was seen, and the planet that has been surprising us ever since. The story of Neptune's discovery is one of the greatest intellectual achievements in the history of science, and it begins with a wobble. By the 1840s, astronomers had been tracking Uranus for decades since its discovery in 1781, and something was wrong. Uranus's observed position kept diverging from its predicted position. Not by much, tiny deviations, fractions of a degree, but persistent, systematic, pointing in specific directions at specific times. Either Newton's laws of gravity were wrong, or something was pulling on Uranus from outside. Two men decided independently to find out what. Urbain Le Verrier in Paris, John Couch Adams in Cambridge, both working alone, both applying the same mathematics. Using the observed perturbations of Uranus's orbit, to reverse engineer the position, mass, and orbital elements of whatever was causing them. This was not a simple calculation. It required solving what is essentially an inverse gravitational problem. Given the effects, find the cause. The mathematics involved were at the frontier of what was computationally possible in the 1840s. Leverrier worked on it for years. In September 1846, Leverrier sent his predicted coordinates to astronomer Johann Galle at the Berlin Observatory. His letter arrived on September 23rd. That same night, Galle pointed his telescope at the predicted position. Neptune was there, within 1 degree of Leverrier's prediction. It was the first planet in history found not by observation, but by the predictive power of mathematics. It was a direct experimental confirmation that Newton's gravitational theory worked across distances and timescales no one had ever tested it on. Adams had reached similar conclusions months earlier, but the British astronomers hadn't acted on his prediction in time. The French got credit for the discovery. The British contested it. A diplomatic incident nearly erupted between France and England over a planet. But beyond the politics, what this meant for science was profound. The universe was, at its deepest level, mathematical. The positions of objects billions of kilometers away could be calculated from first principles. Prediction and observation matched. Neptune's discovery didn't just add a planet to the solar system. It proved that mathematics is the language of the cosmos. And then Voyager 2 arrived and showed us that even the math only gets you so far. Because what was waiting at Neptune, nobody had calculated. Neptune is an ice giant, like Uranus, but with one critical difference: it is alive. Where Uranus appears featureless and calm, Neptune is visibly dynamic. Active cloud systems, dark storm ovals, bright cloud streaks racing around the planet at enormous speed. A planet that looks from the outside like it's doing something. And yet Neptune is colder and further from the sun than Uranus. It receives less energy. By every passive measure, it should be quieter. The reason it isn't comes down to that internal heat. Neptune radiates 2.6 times more energy than it receives from the sun. Its interior is hot, actively hot. Whatever process is generating that heat, gravitational compression of its interior, slow cooling from formation, radioactive decay, it's pumping energy into the atmosphere continuously. That energy drives the winds, feeds the storms, creates the dynamic, visually striking atmosphere that made Voyager 2's images so dramatic when they arrived on Earth in 1989. Uranus, as we covered, has almost no internal heat. Neptune has enormous internal heat, same composition, same size, same distance category, completely different energy output. We don't know why. Neptune's bulk composition mirrors Uranus, a thick hydrogen-helium atmosphere over a vast interior of hot pressurized water, ammonia, and methane ices, a supercritical fluid ocean. Below that, a rocky silicate core. The methane in Neptune's atmosphere, as with Uranus, absorbs red light and reflects blue. But Neptune's blue is noticeably deeper, more saturated, more vivid than Uranus. An additional blue-enhancing compound in its atmosphere, possibly a hydrocarbon haze at high altitude, makes Neptune appear the richest, deepest blue of any planet in the solar system. A color so intense it looks almost unreal, like someone turned up the saturation. And at depth, as with Jupiter and Uranus, diamonds form and rain downward through the interior. Neptune almost certainly has a layer of diamond precipitation accumulating around its core. Millions of tons per year. An ocean of liquid diamond, possibly, at extreme depths. 3 planets in the outer solar system raining diamonds. That is not a coincidence. That is physics. The fastest wind speed ever measured on any planet in our solar system. 2,100 kilometers per hour. That's on Neptune, not Jupiter, not Saturn, not on a planet right next to the Sun. On the planet furthest from the Sun, receiving the least solar energy, in the coldest region of the solar system. The fastest winds in the solar system are in the place that should have the least energy to drive them. This is the Neptune paradox, and it connects directly to that internal heat. On Earth, winds are driven almost entirely by solar energy. Temperature differences created by uneven solar heating drive pressure gradients. Pressure gradients drive winds. Jupiter and Saturn have powerful winds, driven partly by solar energy, partly by their enormous internal heat. Neptune's internal heat is so large relative to the solar energy it receives that the internal heat completely dominates. The atmosphere is driven from below, not from above. The contrast between what the deep interior is doing and what the cold upper atmosphere is doing creates enormous temperature gradients, enormous pressure gradients, and the result is wind speeds that dwarf everything else in the solar system. The winds at Neptune's equator move west, opposite to the planet's rotation. The planet rotates east. The wind goes west at 2,100 kilometers per hour. If you were standing on a platform in Neptune's cloud tops, which you cannot because there is no surface, the wind would be moving past you at roughly 600 meters per second. The speed of sound is 340 meters per second. You would be standing in a wind moving at nearly 2 times the speed of sound, continuously, with no break, no calm zone, just relentless supersonic wind. And within those winds, storms form, dark storms, circular anticyclones, the most dramatic of which Voyager 2 photographed in 1989 and named the Great Dark Spot, a storm the size of Earth, swirling in Neptune's southern hemisphere. It was gone by 1994 when the Hubble Space Telescope looked for it, vanished, without a trace, in 5 years. And in 2016, Hubble found a new Great Dark Spot in the northern hemisphere. New location, new storm, same type. Neptune doesn't maintain its storms like Jupiter does. It creates them, runs them, and dissolves them. The atmosphere is too dynamic, too energetic to let a single storm persist for centuries. The Great Red Spot of Jupiter has lasted 350 years. Neptune's storms last years. Then they're gone. And nobody fully understands why they form or why they disappear. Every large moon in the solar system, every single one, orbits its planet in the same direction the planet rotates. Every one, except Triton. Triton orbits Neptune in the opposite direction, retrograde, going against Neptune's spin. This is not a small irregularity. This is a fundamental violation of how moons form. Moons form from the same disk of material that formed their planet. They form rotating in the same direction. That's how the physics works. That's how every other moon in the solar system formed. Triton did not form around Neptune. Triton was somewhere else, moving in a different orbit, caught by Neptune's gravity at some point in the solar system's history, and captured into orbit. Where did it come from? Almost certainly the Kuiper Belt, the vast region of icy bodies beyond Neptune's orbit. Triton's composition, its density, its surface properties, all match Kuiper Belt objects like Pluto and Eris almost exactly. Triton is, in all likelihood, a Pluto-sized Kuiper Belt object that wandered too close to Neptune and was gravitationally captured. It is the largest captured moon in the solar system, and one of the most geologically active. Voyager 2's flyby revealed a surface of extraordinary complexity. Nitrogen ice plains, pink-tinted frozen nitrogen and methane, strange cantaloupe terrain that looks like nothing else in the solar system, and geysers. Active nitrogen geysers erupting from the surface, shooting dark plumes several kilometers high into the thin atmosphere. On a captured Kuiper Belt object, at -235 degrees Celsius, in the outer reaches of the solar system, active geysers. The energy source is not internal heat. Triton is too cold and too small for significant radiogenic or tidal heating. The geysers are solar-powered. As feeble as Neptune's sunlight is, it's enough to penetrate the transparent nitrogen ice surface, warm a thin layer below, and cause nitrogen gas to erupt upward. A solar-powered geyser at the edge of the solar system. But here's the dark side of Triton's story. Because it orbits in the wrong direction, tidal interactions with Neptune are slowly draining Triton's orbital energy, very slowly, millimeters per year. But in approximately 3.6 billion years, Triton will cross the Roche limit, the point at which Neptune's tidal forces overcome Triton's own gravity. It will be torn apart. Triton will be destroyed by Neptune, and its material will form a new ring system, possibly more spectacular than Saturn's rings are today. The most dramatic event in the future of our solar system. Slow, inevitable, already underway, and we have a front row seat in 3.6 billion years. Voyager 2 flew past Neptune on August 25, 1989. In those few hours of closest approach, it collected more data about Neptune than all previous observations combined. Images, magnetic field measurements, atmospheric composition readings, temperature gradients, moon surveys, and it found something in Neptune's magnetic field that 35 years of analysis has not fully explained. Neptune's magnetic field, like Uranus's, is dramatically offset from its rotation axis, tilted by 47 degrees, offset from the planet's center by 0.55 planetary radii, more than halfway to the surface. This matches Uranus. Both ice giants have wildly anomalous magnetic fields. The leading explanation, that the field is generated in the electrically conducting icy fluid layer rather than in a metallic core, is reasonable and probably correct. But here is what doesn't fit. Voyager 2 detected distinct, localized regions in Neptune's magnetic field where the field lines converged in unusual ways. Not the smooth, dipole-dominated pattern you'd expect even from a tilted off-center field. Patches, irregularities, concentrated field regions that moved as the planet rotated, sometimes aligned, sometimes not. Some researchers have proposed these features indicate a more complex multipolar magnetic field. Not just a tilted dipole, but a field with multiple centers of generation. A chaotic field that's being generated by convective cells in multiple locations in the icy fluid interior simultaneously. If that's correct, and the evidence points in that direction, then Neptune's magnetic field is not just tilted and off-center. It is fundamentally different in structure from any other planetary magnetic field we know. Not a dipole with complications, a completely different kind of field. And the implications go beyond Neptune, because most exoplanets we've detected are Neptune-sized or slightly smaller. The Neptune mass planet category is one of the most common planet types in the galaxy. If Neptune's magnetic field is representative of how ice giants work, and there's reason to think it might be, then most of the magnetic fields we've been assuming for billions of exoplanets are simply wrong. Neptune is not a remote curiosity at the edge of the solar system. It is a template for the most common kind of planet in the universe. And we still don't understand it. We have visited every planet in the solar system: Mercury, Mariner 10, and Messenger, Venus, dozens of Soviet and American spacecraft, Mars, rovers, landers, orbiters, a helicopter, Jupiter, Pioneer, Voyager, Galileo, Juno, Saturn, Pioneer, Voyager, Cassini, 13 years in orbit, Uranus, Voyager 2, 6 hours, Neptune, Voyager 2, a few hours, 8 planets, and the last 2 have had exactly 1 visit each, flyby only, decades ago. The case for a Neptune mission is overwhelming, and has been for years. But Neptune is far. A mission there takes roughly 12 years of travel time, depending on the trajectory. The window for a gravity assist from Jupiter, which dramatically shortens the travel time, opens in the early 2030s and won't return for another 12 years after that. If a mission doesn't launch in the early 2030s, the next viable window is the mid-2040s. The good news: mission concepts exist. The Neptune Odyssey mission, studied by NASA and Johns Hopkins APL, would be an orbiter and atmospheric probe, spending years in the Neptune system. It would orbit Neptune, conduct multiple Triton flybys, and send a probe into the atmosphere. What would it find? The composition of the interior, finally measured directly, not inferred. The magnetic field mapped in 3 dimensions over multiple orbits instead of a single flyby. Triton's geyser fields photographed at resolutions thousands of times better than Voyager 2's images. Evidence for or against a subsurface ocean on Triton. And potentially, data that helps us understand the magnetic fields and interiors of the billions of Neptune-mass exoplanets we've detected around other stars. Neptune is not just the last planet in our solar system. It is the most relevant analog for the most common type of planet in the galaxy. Studying Neptune is studying the universe. We have now covered all 8 planets in the Space Explorer series: Mercury's impossible iron core, Venus's runaway greenhouse, Mars's lost oceans, Jupiter's role as protector and architect, Saturn's dying rings, Uranus's 40 years of neglect, and Neptune, found by equation, driven by mysterious internal heat, guarded by a doomed backwards moon, its magnetic field unlike anything else we know. 8 worlds, each one stranger than we expected, each one full of questions we haven't finished answering. And we are, right now, living in the era when we begin to answer them. Subscribe, hit the bell, and tell me in the comments, which planet in this series surprised you the most? I already know my answer, but I want to hear yours. Until the next mission.